Uh, Thank you, OWASP, and thanks for accepting my talk. And thanks to the moderator, organizers, and pretty much everyone involved. It's really a great journey. I've been into the industry way before OWASP, and I've seen OWASP pretty much from its infancy till what it is now. And it's really great to see the community has grown over the years. Wonderful job to whoever we are behind this. I am not that lucky that or I was not very active in the community, but then I think this is an amazing job, that amazing accomplishment that you guys have achieved over the years. Now, moving on to my presentation, let me get started. I'm just trying to pull up my slides. Okay, here you go. So already Bhuvnesh has covered my intro, but I'll just touch upon what is relevant to this topic that I'm covering today. I'm presenting on software security engineering, learnings from the past to fix the future. So the large part of my experience come from research-focused background. I've been involved in a lot of low-level research, exploratory development, those kind of stuff. But the one that is more relevant is that I also worked in the security engineering side for a little over 10 years. I've led security engineering center of excellence for mid-sized and large-tech companies. I worked closely with the multiple engineering teams to integrate security across SDLC. Lastly, I'm a simple security guy who likes to solve complex security problems using simple methods. Moving on. So the overall, this talk, I have kind of broken down into 4 parts for easy understanding. So I'll start with the history to share some historical data about the known security bugs. I'll provide the reason why we still continue to see 1 to 2 decades old security bugs. I will provide the solution. This may not be the comprehensive solution, but these are the 2 most prominent or 2 best solution, I could say, to implement so that these kind of bugs get taken care over the years ahead. And finally, I'll clear some misconception around software security engineering. Let's start with the history. So most of you, I would say, would be familiar with cross-site scripting, SQL injection. I don't have to give a definition of this. But what I want to highlight is these bugs have been around since a very long time, more than 2 decades. So cross-site scripting was coined in the term was coined by Microsoft in the year 2000, but it was actually found in 1990s. So SQL injection has got a similar history. It was first time mentioned in Frac magazine. And deserialization bug, although it has not been over two decades, but it's pretty much around the same time frame. It was the first time it was reported was back in 2002. And the similar historic bugs you will also find for operating system and OS native apps. Buffer overflow, everyone would be familiar with it. While buffer overflow may seem that it's kind of a taken care, it's not really taken care. It's just that the mitigations are making it harder to exploit. It's just that you're not able to exploit a buffer overflow successfully, but it's still around. It's just that there are so many mitigations around which prevent buffer overflow from occurring. You still see rest conditions. Rest conditions can affect both web applications and OS native application, including operating system. But because it was first found more at a system level, I kept this category here. Use after free, pretty much every single year you find a use after free in a browser or an operating system. So these vulnerabilities are there since near about 2 decades, if not exactly 2 decades. I'd like to share a little snapshot of a large part of these vulnerabilities which have been around since 1999. Now, 1999, it's mentioned as the first record. It's because there was no record maintained prior to it, which is why CV details have mentioned 1999 here, but there are bugs which are found even before that. But what is important to note here is a lot of these bug classes are at a very high level. It's broad classes. You see things like code execution and then overflow bug class. Overflow may include like a buffer overflow, stack overflow, a stack overflow, and a heap overflow, integer overflow. Memory corruption will have, let's say, use after free, double free, those kind of things. So these are high-level bug class names, but what you are also seeing is a lot of these bugs have been around since a long time. Now, these bugs not necessarily mean that this affect a single application or a single software. Basically, these are the count of the vulnerabilities affecting many, many applications and software across the globe, right? So, but you get an idea that these bugs have been around from a very, very long time. So the conclusion here is, one of the things it got to my mind is, what is so wrong with the industry that we have been seeing these kind of bugs from a very, very long time? Why it has not been taken care, which basically is underlying the fact that something is really not right with the way we are approaching towards tackling these kind of bugs. And we'll find out why and how in the following slides. Moving on. So the big question, why do we continue to see 1 to 2 decades old security bugs? So while that could be many reasons, but for the sake of time, I cannot go on, talking about all the reasons I know, but I have only picked 2 most prominent reasons, which actually is the main, or I would say the main root cause for for all these bugs that we have been seeing from a very, very long time. And I'll expand on each of those reasons. Now, before we dive into each of those reasons, the 2 most prominent reasons are obscured within the way the vast majority of the organization respond to a bug report of the application and software that they are responsible for supporting, and they are not responsible for supporting. So what this means is, now I'll expand one by one. Like reason number 1 is, when you get a bug report for a software that you are responsible for, right? The first one is, let's pick this first one here, that you are responsible for a software that you support, you maintain, and you sort of you get a bug report either through a penetration testing company, or a bug bounty hunter, submitted a bug report, or you get it through some other source, or your internal team finds those bugs. There are 3 major ways people will respond to it. There are 3 major ways people will respond to how to fix those bugs. So you fix exactly what is reported, or you fix exactly what is reported, including any other instances of the same bug, or you fix based on a risk rating, high, medium, or low. While this may look fine, but there are some disadvantages associated with such mitigation strategies. So let's talk about each of those disadvantages corresponding to the common mitigation strategy. So let's say you get a bug report, you go and fix the bug, but do not check other instances of or variants of the same bug in the same application, right? So the disadvantage here is, you are likely to miss other instances and variants of the same bug in the application if they exist, right? So you just fixed what is reported, but you didn't care to fix other instances and variants in the same application. The second one is, the second approach is you fix all instances and the variants of a particular bug in an application, but you do not check whether the same bugs also exist in other applications that you support. You did not share that intel with other dev teams that you have, and share that knowledge that, hey, can you go and check if this is the kind of bug that may exist in your application? You didn't do that, but you only fixed for the application that you identified those bugs and you fixed those. So the problem is, again, you are likely to miss instances and variants of the same bug in other applications that you support. The third most common approach for mitigation is, you fix based on a certain risk rating, whether it's a critical, high, medium, whatever the rating could be, CVSS rating and all of that. You fix based on the top ratings, and you kind of park the low rated issues. And when you do that, so what happened is, we have seen historically there are enough evidences where so-called low-hanging bugs, or trivial-looking bugs, can be chained together to perform more practical attacks. So that said, what it basically means is, if these are your mitigation strategies, if these are the strategies that resonate with your mitigation approach, then you are far from any kind of software resilience against known security bugs. Now, when I'm talking about known security bugs, the count that we saw in the CV site, now, when you say it's just your bug, it's not going to affect anyone else, well, you're probably wrong because your application could be used by everyone else. Now, your bug is basically contributing to that global number as well. So when you say your bugs, no one should really be bothered, your bugs is also in a way contributing to that global number, right? Now, moving on to the second reason. The second reason is the way the industry respond to any publicly reported security bug, right? So Microsoft release a patch or release an advisory, Google release an advisory, or Apple release an advisory. So what you do is a typical approach is you see a report and then you check whether it affects your application or software. And if it's no, then you think it's not your problem and you sort of move on and everyone is happy. But if it affects your software, then you go and triage the bug, you assess the risk rating, and you identify whether it's critical or high. If it's critical and high, go ahead and release an urgent fix, make a public advisory, and everyone is happy. If that is not the case, then you sort of a plan for a mitigation at a later stage. So if it's a low risk or medium risk, as I just said, people will generally park it for future fixing, and you, after fixing, you release a patch, everyone is happy, right? That's a very typical approach. Now, while path A, response to security bug, is quite common, it may look very obvious. It may look very common. Path B, while it may look very obvious, this is exactly where the reason is hidden. That why we still continue to see, so many bugs over the years. And I'll expand over it in the following slides. Moving on. Now, this is the solution section I mentioned in the beginning. I've broken down into problem, history, problem, and the solution. So in the solution, I'm going to expand on what that path B means. So learnings from the past, the title, as I said, learnings from the past to fix the future. So here is learning number one. The learning from the historical records of all the known bugs. Now, before I dive into mentioning what that learning is, I'd like to bring your attention to a difference between a bug class and bug nature, because that is relevant in the following slide. So a class of a bug is something that you are familiar with, like OWASP top 10, cross-site scripting, SQL injection. These are the class of a bug. It basically describes in a way a particular bug is exploited. So when you hear cross-site scripting, it doesn't imply immediately what the root cause is. If someone doesn't know what a cross-site scripting is, they hear cross-site scripting for the first time, they could probably make a guess that it probably has to do something with scripting, right? You cannot make a guess that it has got something to do with input validation, because in the name, it doesn't say that. So the class of a bug is more, if you actually see all the class names, vast majority of the class name, they kind of sort of imply the way the particular bug is exploited or its resulting impact. When you say SQL injection, it doesn't say that you are missing parameterized queries. It doesn't say that you are running dynamic query. It says that SQL injection, it has got something to do with the injections. It's the way you exploit the bug. The nature of the bug is primarily relates to its root cause. It may look like that I sort of coined this term, but you will be able to relate to it, what I'm saying in the following slides. So I must admit honestly that I was trying to find a good name for it, and this is what that came to me, that and nature is something like, if you can say that I'm from so-and-so country, that's your class, or yeah, I'm from so-and-so region, that's your class. Nature is your characteristic, right? So looking at those things, I try to relate that to a bug, and I sort of came up with this name. It may not resonate with you, but I thought that's the only thing I could come up with. Now, I already talked about cross-site scripting and SQL injection. What's the difference between class and class and the root cause and the bug nature. Now, moving on, here is some more examples. I'm not going to go through each one of these, but I already covered cross-site scripting and SQL injection. But just to give you one example here, the rest I will leave it for your reading. Anyway, the slides are going to be available, the videos are going to be available. but just take a look at how you need to translate the meaning of a class to its corresponding bug cause and bug nature. And why I'm doing this, you will find out in the following slides. So SQL injection can be translated in a very simple meaning that when a tainted inputs become command, right? So your input becomes command, that's when SQL injection occur. A very simple meaning, a very simple definition of root cause. Now, if you have to put in the bug nature, it's basically an injection flaw at an abstract level, and it is also insecure interpretation of the input, right? Cross-site scripting has got a similar title, a similar root cause when the tainted input becomes output without sanitization, and the bug nature is an injection flaw, right? Now, moving on, I'll keep the rest for you to read later. They will be available on your video, and the slides will be available online. So the way the industry must respond to a publicly reported bug. So we'll expand on part B, which I mentioned is the main reason for where the root cause lies, is when you receive a security bug, you first check, does it affect your application or software, right? And if you think it's no, it doesn't affect, then try to identify the nature of the bug. So you try to dissect further down, deep dive, and try to identify the nature of the bug. Verify whether your application has a functionality or a process that can be affected by a similar natured bug. And if it affects your application, then you obviously have to go and attempt to fix it and release a patch. If it no, then perfectly fine, everyone is happy, right? The other part is the path here, which I already covered. I'm not going to cover that here, but essentially this is how the industry should respond to, and which is where is one of the main reasons. I'll show one example here, and we'll dissect one bug as an example. So here is bug from the year 2000. This is MS00083, right? And if you read here, MS00083, it reads like it's a buffer overflow in the HTTP protocol parser or Microsoft Network Monitor, allows remote attackers to execute arbitrary commands via the malformed data, also known as the netmon protocol parsing vulnerability, right? So the first time you read it, the first thing that comes to your mind is, this is Microsoft bug, not my problem. I'm going to wait for them to come and release a patch. I'm going to install it. I'm happy because this is not my problem. Now, if you read it thoroughly, if you read it carefully, you first see it's a buffer overflow, right? And again, you still think it's a Microsoft bug. You still don't have to worry about it. But if you read further and try to decipher, you sort of start to read that, it's sort of something to do with parsing, because I'm reading something here called, it's a netmon protocol parsing. So now I'm getting a little deep down beyond just buffer overflow. So buffer overflow is the class name here, but here is the nature of the bug is starting to get exposed, right? So you are starting to read something called parsing vulnerability. So let's go through the flow chart here, like how you basically need to get a meaning out of those bug reports that you see publicly. Now, if I have to do a root cause analysis of this bug, first I'll try to identify the bug class, which is basically buffer overflow. Then you try to identify the root cause. And the root cause here is buffer overflow due to several unchecked buffers in the protocol parse, right? And then further deep down, you try to dissect it. Then you sort of separate the meaning here. The nature of the bug is a parsing vulnerability, and the attack vector is a parser functionality. This is very important, parser functionality, right? Now from the buffer overflow till parser functionality, we are here. And then the conclusion basically it implies is, now if you see a number of such bugs across different parser functionality, basically means things can really go wrong with the parser functionality. So the way to look at this bug now is to go and check in your application, do you implement any kind of parser functionality? Is it parsing JSON? Is it parsing file? Is it parsing paths? Is it parsing protocol? Is it parsing anything, basically? It's just a parser, it's a parsing image, right? So you go and check whether you are having the image rendering functionality. You go and check whether you have a JSON parser functionality. You go and check whether you have a network parsing functionality, right? And if yes, then you need to thoroughly test all those instances of those parser functionality, get a thorough testing done, and you would be surprised to see how many issues you find out if you get it professionally tested, right? And what you need to do next is you need to maintain attack vectors database so that you don't lose that intel that you just dissected, invested so much time. You don't lose that information. So all you need to maintain is this, a parser functionality can be an attack vectors, and these are the known set of bugs since like 2000, and these are the way people have been exploiting it, so that in future or in the current situation, if you are doing any design changes, or in future you are trying to make any future design changes for the future applications, then you can always refer back to this attack vector database so that you don't make such mistakes, right? And if it doesn't affect your application, you still need to maintain those records, because in future you never know, you could implement a similar functionality in your application. So it's very important to not to lose that intel that you invested time to dissect and come all the way here. Moving on. So these are some more examples about parsing functionality. Now, these are since year, like MS04 basically means that it's in the year 2004 they released the advisory. MS00 means basically it was released in the year 2000. Again, CV 2004 means it's a year 2004 bug, and same thing. So if you see, these are categorized based on file parsing vulnerabilities, protocol parsing, and path parsing vulnerabilities. But the name that you read here, you will never think that, okay, these are the kind of bugs that could relate to your application. But as you deep dive and try to dissect each of these bugs, you will realize that it will point to some design mistake. It will point to some root cause that is something that you need to map it with your application to see whether your application has got a similar functionality. So all of these bugs are screaming that, hey, we are parser problems, and things can really go bad with parser. So you need to go and check if you are implementing a parser functionality. So the recommendations here is, now you need to do a combing operation. It's hard, but it's not impossible. You need to go back to the CV databases and pretty much all the databases that has been maintaining historic records of the bugs. You also need to refer to Exploit DB or any kind of exploit database which is current, because sometimes there are exploits which for applications which may not have a CV. At least I have seen some of those applications. I don't remember all of those applications, but those are there. So what you need to do is you need to refer to all the CV databases. You need to refer to exploit databases. You need to refer to different vendor databases like Microsoft, Cisco, Google, Apple, and read through that advisory. And you can start from the CV details and start doing a combing operation. And you start deciphering all these bugs, map them to a root cause, and those root cause will be mapped to your functionality. When you're investing that time, over a period of time, you get a hang of it, you improve speed. So it's not like it's sort of going to slow down. You're going to spend next 1 year doing that. It's probably going to take maybe a month's time, few months' time, if you invest 1 or 2% just doing that. And that's going to provide enough intel for you to make solid design decisions when you are doing design changes in your applications or for future applications. You could take those past experience, you could take those past intel, apply on your existing design, and you're most likely to actually take care of all the known bugs in your system if you go ahead and find the different variants and instances of the bug in your application without getting the application tested. So because you already know what the nature of bug and where it could be in your application, and if you know that, you ask your developer, go and fix it if you have implemented it incorrectly, and then you get it tested. So the testing job we are going to get done is going to be more targeted so that you're going to get more precise testing done and more value for money. Always identify variants and instances of the bug. Whenever you get a report for your software, it's not your report or any external report. As I said, you have to dissect and find out whether it affects your application functionalities or not. What you need to do is you need to go and find other instances in your application, and you try to sort of make sure that they are mitigated thoroughly. Moving on, what's the second learning? The second learning is from the way memory corruption bugs have been brought under control in operating system and web browser and OS native apps. So here, I've taken a Windows example, but this is really not a Windows example. This kind of exploit you would see pretty much, for all targets. Could be Linux, could be any target. It could be your mobile phone, Android, iOS. So a typical exploit building blocks looks like this. So you got a trigger for the bug, then there are some jumps, and there's something called NOP-SLED, ROP chain, shellcode. So I'm not going to deep dive. This is not in the scope of this presentation to deep dive into what exploitation looks like. I'm going to, in layman terms, I would say these are sequence of techniques starting from the triggering of the bug till execution of the shellcode. These are sequence of techniques that a program or exploit has to run to make sure that the exploit is successful, right? So these are considered that these are sequence of steps in a layman terminology. So the way operating systems are targeting to break this sequence of steps is they're introducing targeted mitigations to break each of these techniques involved. So if you break the techniques involved, then what will happen is this exploit, even if you find a buffer overflow, even if you find a heap overflow, you find a use app free, you find a double free, you find the most, the most complex bug, but you cannot run a successful exploit in modern operating system. It's getting way too much difficult, because here it's not about hackers against these companies. You are actually talking about hackers against hackers. These companies over the period of time have hired hackers. So these are the people who are observing your bypasses that you're trying to do. They are going back and fixing it and coming back with a new technology that's going to break that sort of a technique. So each of these techniques, like here I have mentioned in yellow highlighting, that these are different mitigation techniques that Microsoft, in this case, I'm just using Microsoft as an example, but a similar concept you'll find for Linux systems and as well as Apple. Even Google implement the same similar technique for browsers. Browsers are nowhere different from operating system. They're pretty much work like an operating system. These are modern mitigations which are going to break the exploit techniques. Now, once your exploit techniques is broken, even if you find a 0-day, chances are you could actually be able to successfully exploit it, right? And largely, there are two different kinds of checks. So one is a behavioral, another one is a non-behavioral. So what I mean by behavioral is, for example, the dog in your house. It does a behavioral profiling of a visitor. So when the visitor is suspicious, it will try to attack, or it will try to stop, or you try to do something, right? It's going to bark or whatever it may do. It does do a behavioral. You understand what it means. It does. It's not like a fixed action of a dog that you will see. A non-behavioral is like a security get. It doesn't do a behavioral profiling. You have access to the get. You can use the access card, or you've got a key. You get in, get out. It's not going to profile the visitor. That's the difference between a behavioral check and a non-behavioral check. Now, there are two behavioral checks here. So one is the ACG, another one is the CFG, which is again going to be deprecated by another modern mitigation called XFG. I'm not going to talk about that in detail. This is outside the scope, but just for your knowledge. Now, in the next slide, I'm going to leave it for reading. This is just to know that these are a list of techniques that Microsoft had introduced in modern operating system to break all those techniques used during common exploitations, right? So as you find new techniques, they will go and improve their mitigation and kill that technique. So I wouldn't be surprised in near future, getting, sort of executing your shellcode or running some kind of exploit on your operating system is going to get so harder that it's going to get nearly impossible. But I'll park that statement for now. So In web applications, why talk about operating system, right? So there's some relation to a web application mitigation. That's why I talked about that, gave that example. Now in web application, the emphasis is too much on non-behavioral checks, which is basically a fixed check, input validation, output escaping, parameterized queries. These are not behavioral checks. These are targeted non-behavioral checks. It's simply check exactly, for a particular kind of a technique. It doesn't really go and profile different variations of the technique and try to stop it. It just simply stop one single technique. That is a limited or no, almost zero focus on introducing behavioral-based mitigation. We don't have a solution that's going to do a behavioral check for the web application. We're not talking about firewalls here. Those are different things. I'm talking about just web application level. Now, there's one or two examples which can be sort of relate to a behavioral check. Is Google reCAPTCHA is a good example where they have machine learning running behind it, and that does some kind of behavioral profiling. When you see, are you a robot or something, you tick it, and it's going to present you with a bunch of things to sort of conform. It's because it's the machine learning that's running behind it. But then that is not sufficient to take care of all sort of application vulnerabilities. It only prevents the sort of automation of the forms. It prevents any kind of brute force attacks. So it has got a very limited capability. So that's really nothing. I can confidently say there's really not many or maybe nothing that can be considered as a comprehensive behavioral solution for web applications or any kind of applications. Now, when I'm talking about behavioral checks here, now, one thing to understand, how do we introduce these kind of behavioral checks? So one thing to understand is an adversary is going to make only finite set of moves. And the reason I have the chessboard next to it is because for every single move you make, if you are playing with the computer has got a finite set of moves that is fed into its database. It try to pull out the best move and try to make the next move. So what I'm trying to say here is when an exploitation occurs, there's only finite set of moves an adversary is going to make. And technically, application or software can be programmed to analyze those finite set of moves an adversary and respond accordingly. So now talking about machine learning here, machine learning has come to a stage where it can be integrated, pretty much it's available off the shelf. You just have to integrate it, and any seasoned programmer can go ahead and leverage machine learning and introduce these kind of checks. So if you could have a database of all the finite set of moves you're looking at after a bug exploitation, you can very well train your machine learning to tackle those kind of bugs. So this session is not really to go deep dive and talk about machine learning and how to do that, but just at a very high level, I can say, if you understand machine learning, if you don't even understand, it has come to a stage that you can simply go and integrate those machine learning APIs and start using it. What you need to do is you need to train it so that you can leverage the machine learning capabilities to go and sort of do those kind of check and prevent those kind of adversary moves. So here is a typical machine learning or a very simple machine learning design. And again, it's just for you to just see, but you just imagine a machine learning is more like it can do behavioral checks if you train it. If you train all the finite moves upon adversary, it can go and check those things and you can apply triggers so that it can even stop. You can apply triggers to stop those kind of malicious actions or any kind of adverse reaction. Now, the final recommendations.
We are way overhead the schedule. Need to quick up.
Okay, so how many minutes I got?
You are over by 2 minutes more. Other panelists are waiting.
All right. Okay. So can I get 2 more minutes, or I'm done?
Mary, you need to. Hello?
Two more minutes, and let's please wrap up. Thank you.
Okay.
Sure.
Thank you.
So I already covered the recommendations. How you need to use machine learning. This slide will be available later on for you guys to go over and understand how to implement it. but I'll cover one of the misconceptions that's been around for years. So the silver bullet in security, software security engineering. Now we are looking at this, sort of a different timeline of when waterfall was introduced, when agile was introduced, when DevOps was introduced. Again, for the sake of time, I'm going to skip through quickly because this is basically to say when security was introduced in all of these life cycles. Now, over the years, DevSecOps have, sort of become very popular, and there has been an increase in misconception around it as well. Well, DevSecOps is a very cool concept, but then again, there's some misconception around it. Now, some of the snippets that are extracted from various online sources is DevOps is, security is better with DevOps, or security gets to introduce early in the DevOps lifecycle, or DevOps is your security team silver bullet. Now, what is wrong with these statements? Now, these statements, if you read carefully, these statements are promoting DevOps in a way that it's way better than any other previous SDLC framework or principles or process. Now, similar statements can be found scattered all over the internet while promoting, DevOps. It is essential, but overhyping can be misleading as well. Now, I'd just like to give a quick snapshot of what basically means building security into SDLC lifecycle. So you have these very common sense, common phases, which is requirements, design, coding, QA, and release. And you try to map security activities with these kind of phases. Now, these can be done with waterfall, this can be done in agile, this can be done in DevOps. So I wouldn't be surprised if there's ML ops and people start talking about ML SecOps. They try to do the same thing, trying to align basically these things with phases. Now, I wouldn't again be surprised that there'll be another next generation software security engineering lifecycle, and you integrate security and sort of consider that as the kind of a silver bullet, because the way DevSecOps have been promoted is it looks like it's sort of been becoming like a de facto standard for security, which is not the case, because all that you're doing is doing this common sense alignment of security stage gate activities across this, which remains fixed across all the development lifecycle, regardless of the lifecycle you use. Now, if you are planning to migrate away from DevOps, what you need to do is you need to do a return on investment and try to understand whether it's sort of favorable for your business needs. If that is the case, then go for it. But if the DevOps is only for security, if you're doing choosing DevSecOps only for security, that's when you need to stop, because you're not going to get any help from DevSecOps for security. If only security is the only reason, because you're probably doing something wrong with your existing lifecycle, existing software development, which you need to go back and check. Now, for the sake of time, I'll quickly skip through this so that because I could say some final notes. This is just to say that going with the flow without rational thinking is not going to lead you to anywhere good. You probably want to ask a lot of questions before going with the flow. Now, building security into the SDL is always a implicit process, explicit process, never implicit. So there is no silver bullet in security engineering, and the level of software security assurance is largely depends on how the security assessment is done at each stages. And a fixed set of common sense activities exist that remains same across all types of development methodology. Sorry, I'm just done. Just one last, some final words. So as I said, just to wrap it up, this session, treat all known security vulnerabilities as a pandemic, especially if they have been around for over decades. And no one wants to see COVID for next 20 years. The same feeling applies to known bugs as well. And if some organization here take away these suggestions to eradicate known bugs in your application and achieve success in eliminating them, then do spread the word and talk about your success. Your organization's success story on eliminating all known bugs will inspire other organizations and potentially lead to some kind of a global ripple effect. And let's reassess the state of all the known bugs in about 20 years from now. Thank you for listening.